All righty, let's go ahead and get started for the day. So the plan is to continue our discussion of heat conduction. So what we did in the last class was we talked about the theory. What we said was, as heat, or as you have some materials, when they get into physical contact, heat can flow from the hot material to the cold material by a means of what's called conduction. And basically, all conduction means is the atoms in the material are oscillating or vibrating. And the hotter the object is, the more energy it has, and thus the greater, the more actively those atoms or molecules are vibrating. And so when you have two materials next to each other, and one of the materials is hotter than the other, that material is vibrating much more strongly than the colder material. And the molecules start running into each other. And so as the object, which is vibrating more strongly, starts to run into the atoms of the material which isn't vibrating as strong, it gives some of its energy through these collisions to those atoms, and thus heat is transferred from one object to another. Right, so that's kind of the mechanism. Now, putting the mechanism aside, we'd like, of course, to be able to analyze different problems and come up with a prediction or a calculation of what we would expect to happen. And the major value we may be interested in when we talk about heat conduction is what's called the heat transfer rate. And that's Q over T. Q being the amount of energy transferred, and T is the time it takes to transfer that heat. And so Q over T means you give 100 joules per second, or whatever it might be. That's the heat transfer rate. The bigger this number, the more heat flows per second than a smaller value. So if you're trying to insulate something, if you're trying to keep your house warm when it's cold outside, then you want to use materials which have a very low heat transfer rate. Because if it's very high, then the walls or the windows or whatever it might be are allowing a lot of the energy that you're trying to keep within your house to flow to the outside, thus cooling off your house, making it colder. And what we know theoretically of the heat transfer rate is that it's equal to Ka delta T over L, where K is called the conductivity of the material. And it's basically every material allows heat to flow more easily or less easily. And so the conductivity is the measure of how easily this material allows the heat to flow through. A greater conductivity, energy can move through it very easily. A low conductivity, think something like styrofoam, it's really hard for the energy to move through the material. And of course, A, that's the surface area. Well, a bigger material, there's lots more places where the energy can escape through. A smaller material, there's only a little bit of places where energy can move through. Delta T is the difference in temperatures between the two edges. So for instance, if we're talking about the inside of the house and the outside of the house, well, the inside of the house is at one temperature, the outside is at another, and the wall or the window is the thing keeping the energy separate. And so a greater difference in temperature, if it's pretty, nice and warm on the inside, but then extremely cold outside, well, that outside is trying to suck the energy out from the house to warm itself up. And so a greater difference in temperature makes the heat transfer rate much higher. Whereas if the outside temperature and the inside temperature are fairly close together, then there's not really this big pressure trying to pull the energy through. And then, of course, the last piece, L, is called the thickness. And as is intuitive, a thicker material, it's harder for heat to go through than a thinner material. You go outside with a thick coat, you'll stay warmer than if you're wearing a thin t-shirt. Even though the material of the two objects might be the same and it's the same size shirt, so everything about it's the same, but if the material itself is thicker, it holds the energy in easier. And so what we did was we did a standard example. Here's a wall. Temperature on the inside of the house is such and such, outside of the house is such and such, and we want to know what's the heat transfer rate through the wall. And of course, another thing to note as scientists is every time we're given an equation, that equation stands for a number of different equations, not just one. So the way I've written this equation is as an equation to calculate the heat transfer rate. But of course, it doesn't have to be an equation to calculate the heat transfer rate. We could calculate anything. We could say, how thick of an insulation layer should we put such that we limit the heat transfer rate to such and such of a limit? Well, in that case, all we would do is take this equation and solve for the thickness instead. Obviously, every one of these variables could be the thing you're trying to solve for. The problem is you have to write down the equation in some way. And so an equation is always written down as something equals something, but that doesn't mean that's the only way to solve the equation. There are other variables there. And those variables could be the things you're supposed to be solving for. And so, for instance, maybe what I'm asking in a question is, how long should you wait for the window to allow 10,000 joules of energy through? Well, in that case, I'm not looking for the heat transfer rate anymore. What I'm looking for is the time. How long should I wait? Given I know the heat that will flow. Q is now a number. So instead, I'm just solving for little t. And so on. So even though the equation's written like this, that doesn't mean the only thing to solve for is the heat transfer rate. Sometimes I could ask for something else, but this is the equation you would use to solve for that thing. So that's what we did last time. Now, what I want to do this time is to talk about what we introduced at the end of last class, which is what happens when we don't just have a single material allowing energy through, but we have multiple layers of different materials. So for instance, what if we have something like this? We have a wall. And remember, when I draw these pictures like this, we're looking at the edge of the wall, the side. We're not looking at the face. So what I mean by that is, over here on this side is like the house, the inside of the house. And over here is the outside of the house. So let's say the outside is at 5 degrees Celsius, and the inside maybe is 30 degrees Celsius. Okay. Well, what if this time we have a second piece of material over here, so that now it's a two-layer system? Maybe it's like a wall and some insulation, or drapes and a window, or something like that. So you have two pieces of material pushed together, and then the left side is where the inside of the house is. You're at a certain temperature. And the right side of this system is where the outside temperature is. And of course, we know he's going to try to flow from the hot side to the cold side. Now, let's say we know some stuff here. What we know is that these two pieces of material are 2 meters by 3 meters in size, and they have a thickness. Let's say the thickness of this first material is 30 centimeters, and the thickness of the second material is 10 centimeters. Okay. So although it's the same size in terms of length and width, the thickness might be different. Also, let's say we know that the conductivity of the first piece is 200, whereas the conductivity of the second piece may be 50. Okay. So for this setup, the questions would go as follows. Part A, find the temperature between the layers. So that means I want to know right here where the first layer meets the second, what is this temperature? I'll call it T3. And then the second thing is, what is the heat transfer rate through the system? Now, for this type of problem, we need to think a little bit because it's not quite straightforward how to handle it. If all I had was the first material, then that's very easy. The heat transfer rate through the first material, I would write down Q over T through the first material is K1, A1, delta T1 over L1, right? I know the area, it's 2 times 3 is 6 square meters. I know the conductivity is 200, delta T. I know the thickness. I can plug all my numbers in and get a Q over T for him. Separately, if I look at just the second material, well, he's got a Q over T. For him, K2, A2, delta T2 over L2. And most likely, these two heat transfer rates are different. The first thing is one material with his own thickness. The second thing is his own material with his thickness. The chances that I would plug all the numbers in and get the same value is fairly low unless I happen to just choose the numbers, perfectly. So each one of these materials has its own heat transfer rate. Once I put them together, how do I figure out the total heat transfer rate? Do I add them? Do I say, well, if the wall allows 200 joules per second and the insulation allows 50 joules per second, is the total heat transfer rate 250? Well, that doesn't really make sense, because if you think about it, in order to get through the second piece, the energy first had to get through the first piece. And of course, you can't get through the first piece unless you also go through the second piece. So it's not like by adding insulation, you're increasing how much heat you can pass through. If anything, you're decreasing it. Once you add this second layer, it should be harder to go through, not easier. So does that mean we should subtract the two heat transfer rates? Well, that doesn't make sense either, because let's say you had two layers that are exactly the same. You have a wall, and then you put a second wall right behind it. Well, the heat transfer rate of the first one, let's say, is 200. The heat transfer rate for the second one is also 200. But if I put them together and what I'm supposed to do is subtract them, then I'm saying that the heat transfer rate through two walls is 0. But that doesn't make sense, because two walls can be thought of as one wall that's just twice as thick. And of course, I could do that calculation and get a number for that. So obviously, there's something weird. There's some way I'm going to have to figure out to take the fact that I have two different layers Each one may give rise to its own heat transfer rate. And when I put them together, this new thing, which is two layers, has some new characteristic. Okay, some new heat transfer rate. How do I figure out what that number is? And that's going to be the secret to the question. The question, or the secret, goes like this. There's many areas in physics and engineering which are going to have something similar. Let's look at circuits as an example. You probably won't get to circuits until next semester, and certainly when you take circuit analysis, that's Physics 323, I teach that course. But just for our enlightenment, let's say we have a circuit, and a circuit looks like this. This thing here is a battery. Okay, this is a symbol we use when drawing circuits, so we don't actually have to draw what an actual battery looks like. This is a symbol that represents a battery, and these are wires, and electricity flows through the wires. And then you can have little things in your circuit. That thing there is called a resistor. Now that can represent a bunch of different things. It could be a light bulb, it could be a radio, whatever it might be. What it does is it resists the flow of current. It makes it harder for current to flow through this circuit than it would have if the resistor wasn't there. If there's no resistor, then the electricity just flows through like nothing. But when we put this object in there, let's say a light bulb that we want to turn on, inevitably it's going to restrict the electricity so that it can do something. It makes the light bulb light up. The old style of light bulbs, incandescent light bulbs that I used my whole life, worked by the fact that the electricity, the current would try to flow through, but the material inside the light bulb is kind of frictiony. It makes it hard for the electrons to flow. And that friction that the electrons are experiencing causes heat. And there's enough heat to heat up a filament so hot that it radiates excess energy in the form of light. And so what we see is the light because of this heat buildup. So obviously, for that to happen, there must be a lot of restriction there, a lot of friction. So that's called a resistor. Well, what if we have two resistors, one right after the other? And let's say this guy, R1, is some value, and R2 is some other value, but I know that R2 is bigger than R1. So it's more resistive than the first resistor. Well, if I try to make my current flow through, what has to happen? Well, the electrons flowing through here have to go through R1 and then have to go through R2 in order to make it back to the beginning of the circuit, which is what circuits is all about. You go all the way through. That's why it's called a circuit. You go all the way through like a race. Well, in order to push these electrons through, the battery is like a pump pushing the electrons. The battery has to push the electrons through the first resistor and then through the second. Well, there's two ways of thinking how this could happen. Either the electrons flow through R1 fairly easily because it's a low resistor, but then as they try to get through R2, they build up because it's really hard for them to make it through R2. So getting through R1 is very easy, so they flow really quickly. But once they hit R2, they slow down, it's hard to make it through, and if this is true, if this is how it worked, then what would happen is you'd have a buildup of electrons as they keep pouring in, but can't make it through the second one until eventually you burn the circuit and the wire melts because of all the electrons sitting there. Well, of course, that doesn't happen. That's not how it actually works. What actually happens is the wire already has electrons everywhere in the wire. So as you start to push on this electron here, it pushes his forward one, his neighbor, and it pushes the next one, and they're all pushing on each other. So as I push this electron to try to make it go through this first resistor, That pushes on an electron that's over here, that's over here, that's over here, that's trying to go through this resistor. So the fact that this electron is trying to make it through this really tough guy, that's going to slow down all the ones prior to him, because they're having to work really hard to push that guy through the resistor. Even though it might have been easy to get through R1, there's a traffic jam. So they're automatically slowed down from the very beginning. It's as if by just having R2 there after R1, the electrons, before they even get there, already feel the effects. Another way of saying it is, let's say you have like you're driving on the interstate and you have a nice wide, 4-lane highway or whatever, and then it constricts to a 2-lane highway. Well, if you woke up really, really early in the morning, then you're flying through this really fast because the 4-lane highway, there's a lot of room. And then when it constricts, you may have to move slower because there's a few more cars there. However, if you wait and you try to go during rush hour, well, there's going to be a backup of cars, a whole bunch of traffic, because all of these cars that are in this 4-lane highway are having to merge into a single or a double lane. And that's going to cause a traffic jam that goes backwards and backwards and backwards. So the effect of this guy is felt by people way back there before they even get there. So they're already slowed down in an area where it should be very fast because of the traffic jam caused by this constriction up ahead. Well, that's what's going to happen with this dual layer system. The fact that I put the second layer there is going to modify how the energy wants to go through the first layer. If the second layer wasn't there, the heat would flow through very nice and fine, however it wants to flow through. But by placing the second layer, the heat can't flow like it would have before. Rather, it'll flow much slower. But more important than that, that's okay. That's intuitive. We can kind of see it. What isn't necessarily as intuitive is that the way this second layer modifies the motion of the energy, the motion of the heat, is to make it so that the heat transfer rate that wants to go through the first layer, Q over T1, is going to be the same as the heat transfer rate that wants to go through the second layer. Okay, now that's not what this number is, or that number. By placing if you have the two objects separate, the two layers separate, each one has a heat transfer rate, some number. However, when I put them together, they both change. The first layer changes his heat transfer rate. The second layer changes his heat transfer rate, such that it's this new heat transfer rate, and it happens to be the same number for both layers. Okay, so it'll be some new Q over T3, not either one separately, some new thing. And if I want to calculate what that new thing is for the system, it happens to be the same number as if I were to calculate the heat transfer rate through this material by itself or this material by itself. Okay, and we're going to see how this works specifically with a calculation. But this is an important concept to understand, and it's a little fickle, but to repeat, if I have one material by itself, I calculate its heat transfer rate, it's Q over T1. Perfect. If I have layer 2 over there by himself, he has his own heat transfer rate, Q over T2. Fine. I put those two layers together, and now I have some new system. Now, what has happened is the fact that these two layers are now up together, each of them affects the other. So the second layer is going to slow down the heat transfer rate trying to get through the first layer, like a traffic jam. And of course, the same holds true for the second layer. The heat transfer rate trying to get through the second layer, well, it had to get through the first layer first. And so the first layer already slowed it down more than it would have before. So the second layer will feel some new heat transfer rate that it didn't have before. What's interesting is that whatever this new heat transfer rate is, they both feel the same number. And whatever that number is, that's the number that makes it through the whole system as a whole system, complex system. So I have to use this concept to try to calculate exactly what I want for this particular example. I have a dual layer system. I'm going to send heat through, and I want to know what the heat transfer rate is through the system. It turns out that in order to do it, I have to use the fact that once I have this complex system or this compound system, multi-layers, Q over T1 must be equal to Q over T2. So let's do it. So let me box this just so you know that was for conceptual purposes, not actually what we're doing here. What we're doing here is we're going to say, all right, part A, I have to use the fact that in a dual layer system, the heat transfer rate for the first layer is going to be equal to the heat transfer rate of the second layer. Okay. And again, generally, this isn't true. You have two different layers. If they're separate from each other, they're completely different heat transfer rates. Once I combine them, it acts as its own little system. It changes everything about how it works. And so now I can make this new equation. Now, of course, I don't know what these numbers are. I have no idea what the heat transfer rate through number one is as a number, nor number two. So what do I do when I get that? I replace what I have there with its equations. So Q over T1 is K1, A1, delta T1 over L1. All the stuff about the first layer. And then that's equal to, of course, all the stuff about the second layer. There he is. And now this I can handle because I was given all the data I need in my question. I know the areas, I know the thicknesses, I know the temperatures. I can do this. So we start. We say, okay, I need the conductivity of number one. That's 200. I need the area of layer one. Well, I'm told this layer has a dimensions 2 by 3 meters. So 2 times 3 is 6 square meters. Now I have delta T1. Now here's the thing about delta T. Remember, delta T means the difference between the temperatures on either side of the layer. Okay, it's tempting to want to do the same thing you did when you only have one layer, in which case it would be 30 minus 5, because you have 30 on one side, 5 on the other. But here we can't do that. Here we have two different layers. For each one of these layers, remember this first part of the equation, the left side here, is only looking at the first layer, ignoring the second layer. Well, looking at the first layer, notice one side is at temperature 30. The other side of the layer is not at 5. It's at whatever this T3 is. Which is why I made part A of this question to calculate T3, because we need to know what this number is in order to solve our problem. Well, for now, I don't know what it is, so I'm going to keep it as T3. So what's the change in temperature? I'm going to say it's the left temperature minus the right temperature, which in this case is 30 minus T3. Now I could have just as easily done the right temperature minus the left temperature, which would be T3 minus 30. That's perfectly fine too. Either way, whatever you chose for the order here, you have to remember that order because you have to do the same one for the right side equation. So here I did the left side of my layer minus the right side of the layer. When I get to layer 2, I have to do it the same way, left minus right again over there. Finally, the thickness. What was the thickness of the first layer? 30 centimeters. Centimeters is bad units. I need meters in physics, so I have to convert 30 centimeters to meters. That's 0.3. And there's the left side of the equation done. Now we move on to the right side. Layer 2, the yellow layer. What's his conductivity? 50. What's his area? It's the same as the first layer. It's 6 meters squared. His delta T, again, because I chose left minus right for the first layer, I have to do left minus right for the second. Well, for the second layer, left is T3 and right is 5 degrees. So for here, it's T3 minus 5. Finally, divide by his thickness, and his thickness was told to be 10 centimeters, so that's 0.1 meters. And now we have an equation. Notice this doesn't tell me Q over T. Rather, this is an equation to calculate T3, this temperature that's between the layers, which is what part A is asking for. So I'm going to use this to calculate T3. So let's go through the process. There's different ways of doing this. Some people will cross multiply these denominators because everybody hates fractions in algebra. But I'll show you a trick. My trick is take these 3 numbers here and simplify them first. And the same goes for these here. Okay, so I'm going to do 200 times 6 divided by 0.3, and that's going to give me 4,000. So those 3 numbers in yellow turn out to be 4,000. The rest, 30 minus T3. So that looks a lot cleaner on the left side than it did before. Having the fraction, the denominator is ugly. But if you simplify the numbers, just calculate them out, it's just one number. That number is 200 times 6 divided by 0.3. Happens to be 4,000 here. Now the right side, 50 times 6, that's 300, divided by 0.1, that's 3,000. So 3,000 times T3 minus 5. All righty. Now we're almost done. It's fairly easy what to do now. We want to distribute through. So I have 4,000 times 30. So that's 12,000, minus 4,000 times T3. 4,000 times T3. So there's the left side. The right side, 3,000 times T3. So 3,000 times T3. Minus 3,000 times 5, 15,000. Next step, of course, collect all the terms with T3 on one side, all the terms without T3 on the other side. So I'm going to move the 15,000 over to the left. So 12,000 plus 15,000 gives me 135,000 on the left. And then I'm going to move the 4,000 T3 over to the right side, and that'll be 7,000 T3. And then, of course, get T3 by itself, divide over the 7,000, and we get 19.29 degrees Celsius. Now, of course, before I box this as an answer, I ask, does this make sense? Well, let's look at the picture. I was told inside my house, which is the hottest part, is 30 degrees. Outside my house is 5 degrees. And I'm looking for what this temperature is in between. Obviously, the temperature better be somewhere between 5 and 30. I look at the answer I got 19. Perfect. It's in between. I can't say it's definitely right. Maybe I made a mistake in my math, but at least I can't say it's definitely wrong. If I had gotten an answer like 52, well, 52 is way hotter than the inside of my house. How in the world could it have gotten hotter when I'm trying to give energy over to the cold side? Or if I got 2 degrees, well, how can in between be colder than the coldest part, which is outside? So this is just a little check, just to make sure you didn't make a major math mistake. You look at this number, does it make sense to the problem? In this case, it does. So, okay, that seems like a good answer to me. I now know the temperature in between the layers. But that's not all that important. What I want is the heat transfer rate. I have this system, a wall and insulation, and I want to know how much energy flows through the system per second. Well, how do I calculate it? I already told you. If Q over T1 is the same as Q over T2, so whatever the heat transfer rate through the first layer is, it's the same as the heat transfer rate through the second layer. That is, whatever that number is, it is the heat transfer rate through the whole system. So if you want to know what it is through the whole system, calculate what it is for one of the layers. Which layer? It doesn't matter. Choose either one you want. Let's say I choose the first layer. All right, part B. I want Q over T. So I'm going to do it for the first layer. K1, A1, delta T1 over L1. K1, 200. A1, 6. Delta T1, remember, 30 on the left minus T3 on the right. But now I know T3. It's not an unknown. So plug it in, 19.29. Divided by L1, which is 0.3. And now check it out. All of this is a bunch of numbers. No unknowns anymore. I could get an actual answer. So I plug this in my calculator. 200 times 6 times 30 minus 19.29, all divided by 0.3. I get 42,840 joules per second. That's how fast the heat transfers through the first layer. It's also how fast the heat transfers through the second layer, which means it's how fast the heat transfers through both layers at the same time. If you would have done Q over T2 as a calculation, you would have gotten the same exact number. And that's how we handle this type of problem. Given a system of multiple layers, in this case we had 2, if we want to know the heat transfer rate through the whole system as a compound system, what do? First, the concept, the thing you need to understand, is that once we put the 2 layers together, the heat transfer rate through the system is equal to the heat transfer rate through either the first layer or the second layer because they're the same number. So the heat transfer rate through layer 1 must be equal, which is what this says, to the heat transfer rate through layer 2 because they're together. So I replace Q over T with the equation for the first layer on the left, second layer on the right. From there, I plug in my numbers given from the problem, and eventually T3 is going to be an unknown in my problem. So I do the algebra, whatever algebra I want to do, as long as it's legal, to calculate the value of T3. Now I know what T3 is. Now that I know that, I choose either one of these layers, either the first one or the second one, doesn't matter which I choose. But now that I know what T3 is, I can plug the number in, and now I have an equation to find Q over T. which solves my problem. So part A is not really all that interesting. It's just the first step to get the answer. In order to calculate the answer, I need to know what T3 is. Once I know it, I can get Q over T. So the first step is calculate T3. That's why I made it part A. Once I've calculated it, I can now do part B, which is the actual question. What's the heat transfer rate? So, any questions about this? Is it making sense? Or you need a little time to soak it in?
It makes sense.
Good. Yeah, it's certainly there's definitely going to be places where little mistakes can be made if you're not careful or the first time you go through it or whatever. So just as is true with all of physics, you have to practice this. Now it's easy to practice because all you got to do is just make up new numbers for these layers, give it a different thickness, make the conductivity different, whatever, or the temperature's different, and then go through it again. The steps are going to be the same. Heat transfer rate through 1 is equal to heat transfer rate through 2. Plug all the numbers in, calculate T3, the temperature between the layers. Once you know that, choose one of the layers and do your normal heat transfer rate calculation for that layer by itself. And then you'll get your answer. So I think that's all I want to do for today. The plans for the future. Our first test, we're not going to have until we're done with the topic of thermodynamics. And so we still have some stuff to go through. In fact, we still have to do radiation, which is probably what we're going to do next time. I may do another example of this and then go to radiation. But once radiation is done, I think we could go ahead and have our first test, which means what we're looking at is if we do radiation next week, then Tuesday of the following, we can have a test review, and that Thursday would be our test. So probably we'll have a test, not this coming week, but the next week. And it'll be an online test. And for those of you who did not have me for first semester, my online tests are handled just like homeworks. So I post the test in the morning, you download it, work it out, submit it back to Canvas by the deadline, and that's that. It's not going to be a timed test or like the automated quizzes on Canvas. It'll be just like you're doing a homework thing, only it's a test. And of course, I'll get into more details as it gets closer. But just so you have kind of an idea of when the test will be, probably in 2 weeks. We have to finish up Thermo. Once Thermo is done, we'll have a test on all of Thermo. So for now, practice this. Make sure you're working to practice problems that are on Canvas to try to get as much practice as possible. And I will be posting a homework for this. I think maybe I already did post it. So yeah, I did. It is posted. I think I have it due Tuesday by 11:59 p.m. So definitely start working on that as soon as you can. And unless you have any questions, you are free to go and enjoy your weekend.
Thank you.
All righty then. See y'all later.